All right, today we're going to talk about how forces interact with things. And so in physical science, we're talking about forces. Now, when we discuss forces, we have to remember that a force is a push or a pull on an object. And so a force has a direction. So if a force has direction, it can be either forward or it can be backward. And if you remember, we call these two things vectors. And so these are called vectors. And so a force is a vector value. And so when we talk about forces, we're talking about things that are vector values. And so that means they have relationships with other vectors as well. And so there's relationships of force with momentum, because momentum is a vector. We also have acceleration, because acceleration is a vector. And our last vector, the first vector we talked about, was velocity. Actually, it wasn't the first vector. The first vector was a D word that has to do with velocity, which is displacement. So from the earliest, displacement, to velocity, to acceleration, to momentum, and now to forces. These are all vector values. And so these are ways we can look. And if you notice, all of those have built one on top of another. And so one of the things that we can look at is actually this relationship of force and momentum. And I just want to briefly go over this. And so when we talk about momentum, if you remember, momentum is mass in motion. And so if mass is in motion, it has a velocity, and that's what we said. We said that this is mass times velocity. But something had to be applied to get that mass into motion. And so to get mass into motion, we also need a force. Forces cause motion. Now, that doesn't mean that forces have to cause motion. Forces can be canceled out, but forces cause motion. Let's say unbalanced forces. Forces cause motion. So when we talk about unbalanced forces causing this motion, to get this velocity, we have to use a force, and that force is usually applied over a certain amount of time. Think about follow through when you're playing a game. Follow through. Think baseball or softball. Even basketball when you're shooting that hoop, or golf. We have to follow through. And so what this does is this follow through actually increases the time the force is in contact with the object. And so if we're increasing the time that the force is in contact with the object, then we end up getting that force and time have something to do with this mass and velocity. And so we can actually call this, we call this thing impulse. In impulse, we use the letter J, and the letter J is impulse, and it stands for force applied by time. And if you think about this, the greater the impulse, the more force is applied and the longer amount of time. The better follow-through you have, the more momentum that baseball or that golf ball or that softball is going to obtain. And so when we talk about impulse, we can say that impulse is equal to momentum. Because this is motion and this is force. And so we've got forces being put into motion, and so this is the relationship between force and motion, impulse and momentum. And we can set those two together. We don't need to really talk about that in too much detail other than the fact that we do have impulse there. And this is a good transition from our momentum unit into our force unit. So let's think about force for a second. So forces are measured in newtons. We abbreviate newtons with an N. And newtons are named after Sir Isaac Newton. And if you recall, Sir Isaac Newton was that guy who had the apple fall on his head out of the tree. He was sitting under a tree and he had this apple and he was sitting there and the apple fell and hit him in the head and he thought, something made this fall down. And so he discovered that gravity had something to do with it. And so Isaac Newton not only discovered gravity, but he discovered that gravity is a force. And so we know that gravity is this really amazing force. And the force of gravity is a relationship of the mass of an object. And so the gravity of an object is, there's a constant. It's related to the masses of two objects divided by the radius between the two objects squared. And so we've got this amazing gravitational formula that Newton came up with. He used things like objects coming together, but he also used planets. He studied the planets and the Earth, and the stars, and the sun, all to come up with this formula. And so basically what gravity does, and what this means is that gravity depends on how close you are, and it depends on how big. All right, so gravity, just in other words, more mass equals more gravity. Think Earth is smaller than Jupiter. Jupiter has a lot more gravity. The moon is smaller than the Earth. The Earth has a lot more gravity than the moon. The moon has less mass. The Earth has more mass. So more mass means more gravitational force. Also, how close you are. So closer together means more gravity. Think about jumping off of a table or jumping off of a building. When you jump off of a building, you're close to the Earth, and so you fall almost straight down. But if you're in outer space, like the moon is still in Earth's gravity, but because it's so far away, it doesn't fall straight down towards the center of the Earth. It orbits around the Earth. And so it's got less gravitational pull from the Earth on the moon than if the moon was right next to the Earth, really close to the Earth. Just like the space station or the space shuttles, which are no longer working, they're not super close to the Earth, so they're not falling straight down. They're falling around the Earth in orbit. It also means that on top of Mount Everest, you have less gravity than you would at the bottom of the ocean, because you're not as close together. At the top of a mountain, you have less gravity than at the bottom of the ocean. Now, what does this gravity mean? Well, the gravity is a force, and we measure the force of gravity by measuring our weight. With weight. Now, you might think we measure weight in pounds. Well, that's an imperial unit. You remember, in science, we don't ever use imperial units. We always use metric units. Well, our metric unit for force is the Newton. And so weight is measured in newtons. Measured in newtons, and we find that weight, that gravitational force. So we find this force of gravity, which is the weight, all right, that force of gravity is equal to the mass. Remember, it has to do with mass, so this is equal to the mass. And it's also equal to the acceleration of gravity. And the acceleration of gravity is the same everywhere on Earth. It's the same everywhere on Earth because it's uniform, because Earth's mass is so big. Earth's mass is so big that it overcomes any other gravities there are because we're so close to it. If we were out in outer space, the acceleration of gravity changes a little bit. But on Earth, the average acceleration of gravity G, we call the acceleration of gravity, is equal to 9.8 meters per second squared. Now, this was tested famously by a guy named Galileo. And a guy named Galileo, he discovered that if he dropped two objects off the Leaning Tower of Pisa, and here he was, he's standing at the top of the Leaning Tower of Pisa, and he's going to drop off two balls, a bowling ball, or he didn't have bowling balls, a cannonball and a tiny ball, a tiny stone. And what he discovered was that both of those objects fell at the same rate. They both hit the ground at the same time. And so the force of gravity, he obviously knew the force of gravity is different because one weighed differently. So why do those different weights fall at the same rate? Well, we know that the acceleration of gravity was the same. And he actually calculated that it is equal to 9.8 meters per second squared. That's meters per second every second. So after 1 second of falling, anything that falls is going to be going 9.8 meters per second. After 2 seconds of falling, everything that's falling on Earth is going to be going 19.6 meters per second. After 3 seconds of falling, it's going to be falling, I can't do that one in my head as fast, 28.6 4. 29.4 meters per second.